Before we move on to the new material, does anyone have any questions on what we've covered so far? All right, well, then we'll start on chapter 2.1, which is page 100 in the book, in your textbook. Going back to your days in geometry, who remembers what a ray is? Anybody? Ray, it's a line, it's a half line is what they're sometimes called, that extends out from a given point. The point from which a ray originates is called its vertex. If you have a second ray that shares a common vertex with the first ray, then the two of them form an angle. Now, when we start talking about these angles, we're going to need to have them. We need to know what we're saying when we communicate with each other. So we're going to start with the standard position for an angle, or two rays with a vertex. If that vertex is located at the origin of a Cartesian coordinate system, with the initial ray positioned on the x-axis, that is defined as the standard position. And that's how we're going to imagine angles when we start talking about them. Well, what we're going to learn first is we're going to discuss how angles are measured and how to convert between different units or between different measures of angles. Who can tell me some of the different ways angles are measured? Degrees? What's another way? Say again? Minutes. Minutes are exactly degrees, minutes, and let's go ahead and finish the set. What's the subdivision of a minute? The second. That's denoted with a double quote. Degrees, minutes, and seconds. These are actually subdivisions of the same measure. Okay? Who can tell me a different kind of measure? Radians. Thank you. Now, why do we have different ways of measuring angles? Why the two different? I mean, it just seems like, is it just some unnecessary confusion? Because, is it like the difference between English and metric? Just out of curiosity, does anyone know what the origin of the degrees of measure? Why are there 360 degrees in a circle, in a full circle? I think everybody knows that. 360 degrees is one full circle, one full revolution. Why? Say again? Okay, you could divide it into 100 degrees or into 400 degrees. So you had 100 degrees for each quadrant. Why did they choose this odd, weird number of 360? I mean, is because it's 6 squared, 60, no, it's not even 60 squared. It's 10 times 6 squared. Yeah, you're on the right track. In the Babylonian calendar, there were 360 days. Each day represented 1 degree of rotation around the sun, or 1 degree represented 1 day in the circle of the year, of their 360-day year. That's why we have 360 degrees in a circle. If any of you are curious, you can come by my office sometime, and I can tell you why they're retired now, but the space shuttles that NASA used to send, technically they're called orbiters. I come by my office sometime, I'll tell you what the orbiter had to do with the backside of a Roman horse. The 360 degrees, that's where that comes from. What about radians? Radians come in because scientists, engineers, physicists, they tend to work in radians instead of degrees because it becomes very convenient for measuring the distance of the arc of a circle. In fact, that's how it's defined. And we're going to look into that. I'm going to jump a little ahead of the book here, but when 2 rays are coincident on the x-axis, and one of them starts to sweep and to rotate around the x-axis, it begins to sweep out an angle theta. We define a positive angle as counterclockwise rotation beginning at the x-axis. Okay? If you talk about a negative angle, whether you're talking radians or degrees, it doesn't matter, but if you have a negative angle, then you're talking about rotating clockwise instead of counterclockwise. One more thing very quickly. You'll notice the Cartesian coordinate system is easily, from the origin, it's handily divided into 4 quadrants. They are numbered in the order that they are passed through by a positively increasing angle. And just a couple more bits of vernacular for you. When the terminal ray of an angle is in the first quadrant, we say that that angle is in quadrant 1. If the terminal ray landed somewhere in the second quadrant, we say that angle is in quadrant 2. Similarly, if it ends up in quadrant 3 or quadrant 4. But if it ends up exactly on one of the axes, let me make sure I pronounce this right. Yeah. If it ends up exactly on one of the axes, it's called a quadrantal angle. Quadrantal angle. This is the nomenclature we use to describe angles. Now, you'll notice one thing about rotation is that it never actually ends. So you can have an angle that's actually greater than 360 degrees. If you talk about an angle that is 450 degrees, then you're talking about an angle that sweeps out. And this is getting messy, so I'm going to start over. Talking about an angle that starts off here it sweeps out 360 degrees, and then what would another 90 degrees would get you to 400, is that right? 450. So the two rays, the initial and the terminal ray of a 450 degree angle would look exactly the same as the two rays that form a 90 degree angle. And you can keep counting as high as you want. What will happen? What would it look like if I drew a negative 270 degree angle? Well, first we've got 360 degrees, so we start at 0 degrees. We go to 90 degrees, 180 degrees, 270 degrees, to 360 degrees, and we continue on and on. So what would negative 270 degrees look like? It would look exactly like the 90 degree, except it would be drawn like that. Now, let's talk about how to convert angles. And we'll start by how do we convert in degrees, radians, and seconds. Well, let's say we start off with an angle of some number, and we're going to need calculators. So 47.4159. How would we go about converting that into degrees? That's in degrees, in decimal notation. How would we convert it into degrees, minutes, and seconds notation? Yep. We start off by noting that we have 47 degrees plus 0.4159 degrees. But we know that each degree is actually 60 minutes. I don't guess I pointed that out yet. But in fact, degrees, there are 360 degrees in one revolution. There are 60 minutes in 1 degree, and there are 60 seconds in 1 minute. So, we now have 47 degrees plus 0.4159 degrees. So we can multiply the 0.415 times 60 minutes per degree. And I can't do that arithmetic in my head. And that gives us 47 degrees, 24.954 minutes, which is 24 minutes plus 0.954 minutes. Nope. Not yet. But now we multiply the minutes by 60 seconds per 1 minute. We end up with 47 degrees, 24 minutes, and 57.24 seconds. How would we convert back from degrees, minutes, and seconds back into decimal notation? We reverse the process. We can say 57.24 seconds depends on how precise your measurement is. But, if it comes up on a homework and you get to 24 seconds, I'm happy that you knew what you were doing. So, okay. Now, if you get out to the seconds and you've got 14,000 seconds, then you did something wrong. That would be a problem. Rounding is, be reasonable when you round. Leave enough information for me to know that you knew what you were doing. We'll be good. We got 57.24 seconds times 1 minute per 60 seconds. So we just divide. And that gives us looky. 0.954 minutes. So we add that to our 24 minutes. 24 minutes plus 0.954 minutes gives us 24.954 minutes, which we then divide by 60 minutes per degree. And that brings us back to 0.4159 degrees, which we add to our, 47 degrees, and we end up back at 47.4159 degrees. And that's why I kept the decimal places, so it would work out the same going backwards as it did going forwards. Okay, we're going to do just a little bit of derivation here. And we're going to look in how we find the length of the arc of a circle. And you might want to pay attention because we're going to use the same technique in a little bit when we look at finding the area of a sector of the circle. Who can tell me what the sector of a circle is? Or if I'm even speaking correctly when I talk about the sector of a circle. Anybody? Sector, piece of pie. Okay. And technically, I really shouldn't say the sector of a circle because a circle has infinite sectors. What we're talking about here is this. Here's our circle. Let's say we have this angle, theta 1, and it's swept out between these two rays. This little section of the circle is a sector. Now, how would you go about finding out the length of that sector? And think about this. Now, if it were a straight line, well, then we could use some trigonometry and sine and cosine functions, and we could find out the length. It probably is some kind of tangent or law of sines or something. But it's not a straight line. It's a curve, which means it is longer than the straight line that connects its two endpoints. Help me out from geometry. Am I wrong? Is that called a chord? C-H-O-R-D? Don't quote me without looking it up first. Okay, but the point here is we want to know the length of that sector, that length of that part of the circle. And to do that, we're going to make use of a relationship that you would have covered in geometry. And I think the book labeled them S and S1. I did it S1 and S2. Yeah. Sorry? They're labeled S. Yeah. Well, from a relationship we learn about in geometry, we find that the ratios of these are the same. So if we can say, we know that theta 1 divided by theta 2 is equal to S1 divided by S2. And that's our starting point. Now, forgive me, but I want to try and do this as closely as I can to what the book does, so you can reference it. And you won't be. And I don't want to give you some information that would confuse you. No, they're throwing in something here. Did I skip something that I shouldn't have? If I did, I can go back and cover it. Yeah, I left out the definition of a radian. I left out the definition of a radian. I told you that 360 degrees is one circle, but a radian is defined such that if a circle has a radius r and you take and sweep out a sector of that radius, that is also the same length as the radius, then the angle subtended by that sector and by the ratio of that sector to that radius is defined as 1 radian. Hence the name radian. It's the angle that sweeps out a sector of 1 radius's length. Okay? Does everyone understand that?
So radians never the same size?
Radians are always the same size.
No, that's not. I guess that's not my question. Sector is not always the same size to define a radian.
No, it's not.
That's the question.
The sector depends on the radius. If you go to a larger radius, then you will get a larger sector.
Okay, that's part of the question. The other question is the angle will change. The angle can also change to define a radian.
No, an angle can be described as a different number of radians. So if you're talking about this angle, that would be a half radian. And if we haven't gotten there yet, but if you go all the way over to 180 degrees, then you'll get exactly pi radians.
I understand that part. You have a radian already established. You're starting to, if you already knew what the angle was, then you couldn't have a radian, right? Why would we have to worry about theta?
Well, let's back up and try not to confuse anything here.
There's not a set numeric value for one radian.
Well, there will be, but the definition of a radian is not a set numeric value. It is defined as the angle that is subtended between the endpoints of a sector that is equal in length to the radius of the circle. No. We're not trying to say, we're saying here at this point, we're not talking about how many degrees are in the radian. Okay, we haven't gotten there yet. What we're talking about is the definition of the radian. However many degrees it is, it's that angle that you have to sweep out between the two rays, between the initial and the terminal ray, in order for the sector that they sweep out to equal the same length as the radius. So that 1 radian is equal to the sector divided by the radius. When the sector is equal to the radius. So you end up with 1 radian. If you divide the sector that is swept out by the radius, when the two are exactly the same length, the angle between them is 1 radian. That's the definition. Now, let's go back over here and hopefully some of this will start to click. Now let's assume here that this is equal, this theta 1, in this over here, let's get back over here. Let's assume that theta 1 is equal to 1 radian. Then that means that S1 is equal to the radius of the circle. It's a ratio, it's a proportion. We're looking at the proportions here. Because the ratio of theta 1 to theta 2 is equal to the ratio of S1 to S2. Well, if we assume that theta 1 is 1 radian, then we know that S1 is equal to the radius of the circle. All right? Now, Another thing I want to point out to you, and it comes back over here to this definition of a radian. What, and I want you to think about this, and I seriously want you to answer this. What are the units of a radian? Because as Val very astutely pointed out, we haven't defined any number of degrees here. All we did was define the ratio of a length divided by a length. You're very close. Strictly speaking, radian is unitless. It has no units. It's just a ratio. Say again? Yeah, they don't, well, they're, yeah, exactly. Kelvin actually kind of is the unit, but yeah. So we can, now people will talk about an angle of so many radians. But when you're doing calculations, units become very important. You cannot add two numbers together if they are different units. Okay, you can't add you can't add 16 degrees Fahrenheit to 12 inches. I mean, it wouldn't be, you could add 16 and 12, but it would be meaningless in terms of, okay? The point here is that radians are unitless. They don't have units. Now, degrees are units. We talk about a degree as being a fractional part of a circle, of one revolution. So a degree is a unit. That's why when you, and this is, when you write out numbers of angles, you would write out that it is 24.6 degrees. Or you would write it out as 24 degrees, so many minutes and so many seconds, and you would put the little circle, the little apostrophe, and the little double apostrophe. But when you write out an angle in radians, you don't put units on it. You just write the number because the radians have no units. They're just a ratio of two lengths. This is a distance of so many inches or feet or whatever, and this is a distance of so many feet or inches. And when you divide x inches by y inches, the units cancel, and you end up with a unitless ratio. Same thing here. So I just want to I want to point this out so you don't think I'm pulling a fast one here when I just drop the word radian and I rewrite this equation. That one radian is truly a unitless number. But the ratio of that number to theta 2 in radians is equal to the ratio of the radius of this circle to the length of the sector subtended here. That means we can now do some algebraic manipulation there, multiply both sides by theta 2 and both sides by S2, and we end up with the sector S2 is equal to the radius times the angle it's subtended. And it's really just going back to the very definition of a radian. If you want to know the length of a sector that is swept out by two rays forming an angle of x radians, then the length of the sector is simply the radius times the angle in radians. Does everyone understand why it's important to recognize that radians are unitless? Does anyone not understand why it's important? When you start doing actual measurements, you don't just measure 12. You measure 12 feet. Or you measure 10 volts. Or you measure 352 degrees. Okay? If you want to know how fast you're going, you start by measuring a distance, so many miles. And you divide that distance by how long it took you to travel it, so many hours. And you end up with a number, a ratio that is expressed in units of miles divided by hours, or miles per hour. When you start dividing numbers, or multiplying numbers, it's important to keep track of the units. I would go into more depth on this if this were a physics class, but it's a trig class. Go ahead.
If the radian is equal to radius, if there's 24.6 radians, would that be multiplied by whatever the radius was?
Ask that one more time.
You said the radian was equal to the radius.
No. It's not equal. The radian will vary depending on how big the angle is. It'll start from 0 radians, and what we're about to see is that if you go all the way around the circle, you get to 2 pi radians. So the number of radians depends on the angle. It's a measure, it's an expression of the angle. Just like degrees. And we're going to convert radians to degrees and degrees back to radians here in just a bit. So you'll see how they relate to each other. But right now, it's just an angle. It doesn't have units, it's just an angle. And if you multiply the radius of any circle by a number of radians, then that will tell you the length of that circle's sector that's swept out by that angle in radians. Okay? Let's trudge on, and hopefully this will start to click. And for any of you who are still confused by this, my office is down the hall. I'm there pretty much all day. When I'm not in class or in a lab, I'm down there. So if you're confused, if you have questions, come find me. Now, that is the arc length, the length of the sector. What if you went a full circle? What if you started out here and you swept out a complete circle? What would the length of that sector be? It would be 2 pi radians. How do you find the circumference of a circle? Radius times 2 pi. The circumference of this circle is equal to 2 pi times the radius, which we now know is equal to theta of a full circle times the radius. So in terms of radians, if you have an angle that is 2 pi radians, you are basically saying that you've gone full circle. And that gives you the... Now, what if you only went halfway? What if you stopped here? Would be pi radians. If the whole circle is 2 pi radians, then this would be pi radians. If you only went 90 degrees, half pi, or pi over 2. What if you went all the way down to 270 degrees? Pi and a half, or 3 pi over 2. And there's 2 pi. What if you went 3 pi? Where would you be? No. At 180. If you went 4 pi, you'd be back at 360. There's a relationship here. For any integer number of pi, if the integer is odd, it ends up at 180 degrees. Now, that doesn't mean the angle is 180 degrees. The angle could be many times 360 degrees, but if it's odd, if it's an odd number of pi, it ends up on the 180. If it's an even number of pi, it ends up on the 0, back where you started. Now, what we need to be able to do next is convert from radians into degrees. Well, okay, let's see how... let me go back to the book. I want to make sure that... Yeah, okay, they do it pretty straight for me. We have... We have one full circle. And we know that that's equal to 360 degrees. And we also know that that's equal to 2 pi radians. Well, we divide both sides by 2, and we find out that 180 degrees is equal to pi radians. We divide both sides by 180 degrees, and we find out that 1 is equal to pi over 180 degrees. So there are pi radians per 180 degrees. Now, if you want to say we've got 90 degrees, and we wanted to convert that into radians, and we simply multiply by pi radians for 180 degrees, and that gives us 90 divided by 180 is 1/2 pi, or pi over 2, which we'd already seen because we counted them. What if we want to convert from radians back into degrees? What if we've got a weird number? Say we've got a weird number of, I don't know, let's say pi over 3. We've got pi over 3 radians. How many degrees is that? Well, we know that pi radians divided by 180 degrees is 1. So we can algebraically manipulate that to take the reciprocal, and we get 180 degrees divided by pi. So if we want to go 180 degrees is equal to pi radians, so we can, taking the ratio is just multiplying by 1. So we multiply 180 degrees divided by pi. The pi's canceled. We end up with 180 divided by 3. How many degrees is that? 60 degrees. Pi over 3. I happen to choose pi over 3 because that's one of the nice numbers that they give you a table of them in the book here somewhere. Let me find it. There it is, table 1 on page 106. They list a bunch of nice even fractions of pi that work out to nice even numbers of degrees. But these conversions do not require this. If we wanted to convert pick a random number of degrees, 46.159 degrees. How many radians is that? You multiply it by pi radians per 180 degrees, and you get 46. 46.159 divided by 180 gives you somebody 0.256 radians. So if you have a circle, oh man, I really need to go through here and clean out all these dead markers. If you have a circle of radius 14 feet, and you have an angle out of that circle of 46.159 degrees, how would you find the length of that sector? You would convert 46.159 degrees into 0.256 radians, and then you would multiply 14 feet by 0.256 radians, and that would give you, somebody with a calculator? I keep seeing people. Say again? 3.59. 3.59 what? Feet. No, radians are unitless. All we did was we multiplied feet by something unitless, which means we're left with feet. The length of that sector. Everybody see how that's done? What if you had an angle that was defined as, and everybody get ready on the calculators because we're going to actually do some here. We're going to do some arithmetic, which is a polite way of saying you're going to do some arithmetic. Start off with an angle of 4.1 radians. Let's convert that into degrees, minutes, and seconds. We start with 4.1 radians. How do we convert it into degrees? Just a decimal notation of degrees. We multiply by 180 degrees divided by pi radians. Now is when it would be, you would start worrying about rounding off after a few decimal places. What do we have here? Say again? Well, but do the division. Divide by pi. 234.91 degrees. Because we multiplied by degrees. Which is equal to 234 degrees plus 0.91 degrees. How do we convert that 0.91 degrees into minutes? Times 60 minutes per 1 degree gives us, say again, how many? 54.6 minutes, which is 54 minutes plus 0.6 minutes that we want to convert to seconds. So we multiply by 60 seconds per minute. Yeah, it would be, wouldn't it? 36. Well, that was convenient. 36 seconds. Oh, don't really need the plus signs anymore. So we started off with 4.1 radians and miraculously found out that it worked out to an even 234 degrees, 54 minutes, and 36 seconds. We could then reverse, could we then reverse this conversion and go back from degrees, minutes, and seconds to a decimal notation of degrees, which we could then convert back into a number of radians? All right, before I go on to the next section, are there any more questions? Anyone have any questions of what we covered up to now?
Are you always going to use 180 over pi to convert to?
I am. You could come up with any arbitrary ratio that's equal to 180 over pi or pi over 180. The trick is that 180 degrees is equal to pi radians. So anytime you multiply by that ratio, you're actually, algebraically, all you're doing is you're multiplying by 1, which is an identity, unit identity. So if you multiply anything by 1, you end up with the same thing. The only thing that changed is the units. See what I'm saying? That's what's important when you start doing conversions. You're multiplying a ratio of different units, and you're converting from the units that you have to the units you want. But the ratio that you multiply by has to be, they have to be equal above and below, but that's what gives it a ratio of 1, which means you're not actually changing the value, you're changing the number to express the same value in different units. Okay, any more questions? All right, well, then let's talk about the last part. I think this is the last part for this section. Yep. No, not quite. We got one more thing after this. Fortunately, this is very simple, or not necessarily simple. I guess that depends. What I want to talk about now, and that's a good place to start. We have a circle with a central angle theta that subtends some arc length of the circumference of the circle. Now we want to know what is the area of this sector. Okay, so let's start with the same way we did before, using that same ratio. Again, going back to geometry, we know that the ratio of these values are the same. So we can say that theta divided by theta 1 is equal to area divided by area 1. And again, we already know from algebra and geometry the area of a complete circle. How do you calculate the area of a full circle? Pi r squared. MR dux. You never heard that? Have you heard that? M-R dux. A-R not. O-S-A-R. C-M wangs. Y-I-B. M-R dux. Come on, there's got to be room in your life for a little levity. All right, pi r squared. That's the area of a full circle. So let's assume that this area of this full circle, let's assume the area A1, that don't matter. Let's say the area 1 is a full circle. Pi r squared. What does that tell us about theta 1? The angle that subtends a full circle. Yeah, but we're in radians. 2 pi. Okay? So we know that theta divided by 2 pi is equal to the area A divided by pi r squared. Let's solve for A. And we end up with multiplying both sides by pi r squared times the angle theta in radians, which is divided by 2 pi. The pi's cancel out, and we're left with the area of the angle subtended by theta, of the sector subtended by the angle theta, is equal to 1/2 r times theta r squared. Okay, this is a formula that you might want to write down. The area of a sector of the circle is equal to 1/2 r squared theta. Oops, sorry. S, the sector length of the arc, is equal to r theta. The area of that circle that's swept out by the same angle is equal to 1/2 the radius squared times theta. When theta is in radians, if theta is given in degrees, these formulas don't work. Okay? This is why engineers and physicists like to use radians instead of degrees. Now, let's talk about the speed of an object moving in a circle. I didn't just nut up my little recorder back there. Still following? Okay. Thing nutted up on me yesterday, and I didn't get any of my classes to post online. We're going to talk about angular speed, or the speed of an object moving in a circular path. Okay, they start with the simple definition of velocity, which speed. We'll call it v because s already means the length of the arc. So velocity is equal to distance divided by time. Okay, well, what if the distance we're measuring is not a straight line, but is a path along a circle? Then we would call that distance an arc length, or S, divided by unit time. Now, I'm going to introduce a definition. Call it the Greek letter omega. And we're going to call that angular speed. And that is equal to the number of radians that are swept out per unit time. Okay? All that's saying is, if you go 2 pi radians in 1 second, how fast are you going? You're going 1 full revolution for every second, or 1 RPS. And how fast would that be in minutes? 60 revolutions per minute, or 60 RPMs. Okay. Yeah, I'm not going to even talk about hertz. If you're how many of you are in here in the electronics program? Electrical? Okay, then you do know about hertz. So the same thing, hertz, would be cycles per second. 2 pi radians per second would be 1 hertz. 1 full circle per second. Okay? This is angular speed. Well, if we want to talk about the linear speed in terms of feet per second that an object is traveling around this circle, and we know the radiuses are feet, then we know that the arc length that is swept out, S, is equal to what? What's the length of the arc? Radius times theta, exactly. R theta divided by T. That gives us the linear speed in feet per second, because radius is measured in feet, of an object traveling in that circular path. But look right here. What is theta divided by T? That's the definition of angular velocity. So the linear velocity of an object traveling in a circle is equal to the radius of the circle times omega. That little funny W is the lowercase Greek letter omega. And it stands for angular speed, or radians per second. If you have a number that's expressed in radians per second, how would you convert it into degrees per second? Or maybe ask the question the other way around. If you have a measurement, let's say you know that your engine is running at 1800 RPMs. How fast is the surface of that shaft actually spinning? Could you convert RPMs, or revolutions per minute, into omega, into angular speed of radians per second? If you have 1800 RPMs, that's pretty decent idle speed, isn't it? Maybe a little fast. Doesn't matter. 1800 revolutions per minute. How many radians per minute is that? That's 1800 full revolutions. 1 revolution is, 2 pi radians. Nope, don't need it. Two pi radians per 1 revolution. So 1800 times 2 pi gives you somebody do the arithmetic, please. 11,309, and we'll cut it off there. Not degrees, radians per minute. And we know that each minute, let's go ahead and write the units in so as not to confuse anybody. This is radians per minute. Now, if we multiply 1 minute divided by 60 seconds, so 11,309 divided by 60, the minutes cancel. What's 11,309 divided by 60? 188.4, okay, 188.5. Radians per second. That's your omega. That's the angular speed of the shaft of your engine when it's idling at 1800 RPMs. Now all you have to know is the radius of your shaft. Multiply, what's a good shaft radius for a drive shaft on an engine? A couple of inches. Okay, well, let's say it's 2 inches. Then the radius is 1 inch. So the radius times omega equals 1 times 188.5. Say again? Yeah, I know. Measuring it at the end, the concentric end, yeah.
Okay.
Forget about the lobes and the offsets. But you would do the same thing if you wanted to measure, if you wanted to know how the linear speed of that offset. What radius is it? And that'll give you the speed. The radius times that angular speed, in this case, because we chose 2 inches, the radius is 1, so it becomes 188.5 inches per second. Questions? Comments? Hey, has everybody seen the assignment on Canvas? Okay. Hey, wait, before y'all leave, quick question. Does anyone know if we're going to have class on Monday? Our classes? No classes on Monday? Monday's a holiday. Bonuses, thank you. Thank you very much. I've been meaning to tell you this. I want all of you to know you can earn bonus points throughout the semester. Each week when you do your homework assignment, after you complete all of the assigned problems, okay, so don't do half of the assigned problems and then try to earn a bonus point. Once you complete all of the assigned problems, pick one additional problem. Your choice. Work it. I will give you 2 bonus points for each one, but you can only do 1 per week. So at the end of the semester, there's 13 weeks left, 14 weeks, you can pick up another 26, 28 points of bonus points. I'll keep track of them off book. They may help you at the end of the semester get over that last little bit to get the next grade up.
Is there a sign-in sheet on this?
There is. would you please tear one out of your tablet and everyone sign in before you leave? Oh, that's yours.
Yep. I'm here.
Sorry, slow you all down, right?
No, you ain't.
I did it intentionally. You guys jumping up.
Oh, you betcha. Thank you. Do a makeup test. When is it convenient for you? You got an hour? I'll put you in the classroom. You can take it right now. Say again?
I've missed quite a bit, I guess. I haven't been here for the first 2 weeks.
Yeah, you missed a little bit.
I can't make up here.
Yeah, you can.
I can.
Sure.
I can still do homework assignments and all that.
Yeah, they're on Canvas.
Okay.